Hey NEET aspirants, welcome Physics for NEET. Physics, in its essence, is the study of the universe and the fundamental laws that govern it. To comprehend this vast and intricate cosmos, we need a language that transcends cultural barriers and allows us to communicate ideas with clarity and precision. This language is built upon the foundation of physical quantities, units and dimensions. Just as letters form words and words form sentences, physical quantities, measured in units and expressed through dimensions, form the fundamental building blocks of physics. Imagine trying to describe the universe without a common understanding of distance or time. How would we convey the sheer scale of galaxies or the fleeting lifespan of subatomic particles? Units and dimensions provide the necessary framework for quantifying and comparing physical phenomena. They enable us to express observations in a standardized manner, fostering collaboration and advancing our collective understanding of the natural world. At the heart of physics lie fundamental quantities, the bedrock upon which all other physical concepts are built. These quantities are fundamental because they cannot be defined in terms of other quantities. They are the atoms of the physical world, indivisible and independent. Examples of fundamental quantities include length, mass, and time. Length, the spatial extent of an object, allows us to measure distances between stars and the diameter of atoms. Mass, a measure of an object's resistance to acceleration, helps us understand the gravitational pull of planets and the inertia of a moving car. Time, the relentless flow from past to present to future, allows us to track the motion of celestial bodies and the decay of radioactive isotopes. These fundamental quantities, along with a few others like electric current, temperature, and amount of substance, form the foundation of our physical descriptions. They are the independent variables in the grand equation of the universe, and their precise measurement is crucial for unraveling the secrets of the cosmos. While fundamental quantities provide the building blocks, it is the derived quantities that truly enrich our understanding of the physical world. These quantities, as their name suggests, are derived from fundamental quantities through mathematical relationships. They represent combinations of fundamental quantities, allowing us to describe more complex phenomena. Consider speed, for instance. It is defined as the distance traveled per unit of time. Here, distance, a fundamental quantity representing length, is combined with time, another fundamental quantity, to give us speed, a derived quantity. Speed, in turn, can be combined with other quantities to derive even more complex concepts like acceleration, momentum, and kinetic energy. The beauty of derived quantities lies in their ability to capture the interconnectedness of the physical world. Just as a symphony orchestra combines individual instruments to create a harmonious whole, derived quantities weave together fundamental quantities to reveal the intricate relationships governing the universe. From the simple act of walking to the complex dynamics of a black hole, derived quantities allow us to quantify and comprehend the physical world in all its richness and complexity. Having established the concept of physical quantities, we now turn our attention to units, the tools that make these quantities measurable and meaningful. Units provide a reference point for consistent measurements. For example, the meter is a unit of length, ensuring everyone understands the table's size. Similarly, the kilogram is a unit of mass, and the second is a unit of time. Each unit represents a specific amount of the corresponding physical quantity. Over the centuries, different systems of units have emerged, each with its own set of base units and conventions. This proliferation of systems led to confusion and hindered scientific communication. To address this issue, the International System of Units, or SI, a modernized version of the metric system, was established as the global standard for measurements. The SI system is built upon 7 base units, each representing a fundamental physical quantity: the meter for length, the kilogram for mass, the second for time, the ampere for electric current, the Kelvin for temperature, the mole for amount of substance, and the candela for luminous intensity. The SI system offers several advantages over other systems. It is a coherent system, meaning that units for derived quantities are obtained consistently from the base units, eliminating the need for arbitrary conversion factors. It is also a decimal system, making conversions between units as simple as moving the decimal point. The widespread adoption of the SI system has greatly simplified scientific communication and fostered international collaboration in research and technology. Dimensional analysis is a powerful technique that goes beyond simple unit conversions. It allows us to check the consistency of equations and derive relationships between physical quantities. At its core, it involves examining the dimensions of physical quantities. Every physical quantity can be expressed in terms of length, mass, and time. For instance, speed is distance over time. By analyzing dimensions, we ensure equations are consistent, understanding errors, precision and accuracy in measurements. In the pursuit of scientific knowledge, measurements are the bridge connecting theoretical models to the physical world. However, no measurement is perfect. Errors, inherent in any measurement process, introduce uncertainties that must be acknowledged and understood. Recognizing and minimizing these errors is crucial for obtaining reliable and meaningful results. Measurement errors can be broadly classified into two categories: systematic errors and random errors. Systematic errors, as the name suggests, arise from consistent biases in the measuring instrument or the measurement process itself. These errors tend to shift measurements in a particular direction, leading to results that are consistently higher or lower than the true value. Random errors, on the other hand, are unpredictable fluctuations in measurements that arise from various uncontrollable factors, such as environmental conditions or limitations in our ability to read instruments. Unlike systematic errors, random errors cause measurements to be scattered around the true value, sometimes higher and sometimes lower. When reporting measurements, it is essential to convey not only the numerical value, but also the associated uncertainty. Significant figures provide a concise way to communicate the precision of a measurement, indicating the digits in a number that are considered reliable. The number of significant figures in a measurement is determined by the precision of the measuring instrument and the way the measurement is taken. For example, if a ruler has markings down to millimeters, we can reliably measure lengths to the nearest millimeter. If we measure a length to be 12.3 centimeters using this ruler, our measurement has three significant figures. The last significant figure in a measurement is always uncertain. In our example of 12.3 centimeters, the last digit, 3, is uncertain because the actual length might be slightly above or below that mark on the ruler. Significant figures are crucial for performing calculations with measured quantities, ensuring that the final result reflects the precision of the original measurements. While the SI system has gained widespread adoption, other unit systems are still in use in various fields and regions. Converting between different unit systems is often necessary, especially when dealing with legacy data or collaborating with researchers using different conventions. Unit conversions, while seemingly simple, can be a source of errors if not performed carefully. The key to successful unit conversion lies in understanding conversion factors. A conversion factor is a ratio that expresses the equivalent values of a quantity in two different units. For example, the conversion factor between meters and centimeters is 100 centimeters per meter, indicating that 1 meter is equivalent to 100 centimeters. When performing unit conversions, it's crucial to ensure that the units cancel out properly, leaving the desired unit in the final answer. This involves multiplying the original value by the appropriate conversion factor, or a series of conversion factors, treating them like fractions and cancelling out common units. Units and dimensions are the warp and weft of physics. They hold the entire fabric together. From subatomic particles to galaxies, our understanding relies on quantification. Units provide the language, while dimensions offer deeper insights. Mastering them is about intuition and appreciating precision in science.